Okay, so today we are going to talk about backpropagation. My name is Hazrat and I'm a lecturer in AI at the University of Stirling. So before we proceed with the lecture, it's good to remind some of the notations that we use here. For example, W represents the weights of the network, then Wij superscript L represent the weight from unit J in layer L to unit I in layer L plus 1, and then we have J of W, which is the cost function for this network, and then we have the partial derivative of J with respect to W. Then we have the data which we represent as X. So if we have n number of features in the data, we represent it as x1, x2 up to xn. Here we rather assume a simple case, a data where we have only two features, so n equal to 2. And then we have Z superscript L subscript 2, which is the weighted sum in unit number 2 in layer L. And similarly we have A2 superscript L, which is the activation value in unit number 2 in layer L. And finally we have the error associated with a unit in each layer. So for example, delta J superscript L will represent the error associated with unit J in layer L. So backpropagation is a method that enables us to efficiently compute the gradients. So what is our goal? Our goal is to optimize the cost function, or we say minimize the cost function J of W. So we need to find out the optimal choice of W's, and to use any optimization algorithm here, we need the partial derivatives of J with respect to W. So it's good to start with a quick reminder of forward propagation before we switch to back propagation. So for example, for this network where we have 4 layers, one input layer, 2 hidden layers, and one output layer. So we know that in the activation in each unit is basically computed as such. So we compute Z1, which is a weighted sum. So for example, looking at here, let me highlight it. So looking here, we compute the Z1 superscript 2, and then we apply the activation function to compute the value of A1 superscript 2. Similarly, in the next layer we have then Z1 superscript 3, which is the weighted sum in this unit, and then we have the activation value, which is basically computed by applying the activation function on this weighted sum. And finally we have the output unit in the output layer. So we have the weighted sum represented as Z1 superscript 4, and finally the activation value in this unit is A1 superscript 4. So let us focus on one particular unit in hidden layer, so layer number 3. So let us focus on this unit where we have the weighted sum represented as Z2 superscript 3, and we can calculate it as here shown here. So we can calculate this by multiplying the weights with the corresponding units in the previous layer and then summing them up. And finally we compute the activation value here by applying the activation function. Okay, so the input to this activation function in this case is the weighted sum. And the backpropagation now does the computation in a reverse direction. So until now we were moving from left to right or from input to output, but the backpropagation will go from output to input, and it will basically propagate the error associated with each unit. So let's say we represent the error by delta superscript L subscript J. So that is the error in layer number L and unit J. Okay, so this error is basically computed as a partial derivative of the cost function for all J greater than 0, but we will look at it in more detail now. So if we look at the error in the output layer, so it's simply, we can say, the difference between the desired output and actual output. So the actual output by this unit was A1 superscript 4, and the desired output was the values of Y that we know in advance. So simply for each input sample, the difference between these two can be regarded as the error. in very simple terms. So we now have the error associated with this layer, and we propagate this error in the backward direction. So for example, if we focus on this unit, so we focus on this unit here, so we can compute the error associated with this unit as delta superscript 3 subscript 2, which is the error in unit 2 in layer number 3. So now we see that we can propagate the error in the backward direction here as shown by the dashed arrow, and we multiply it with the associated weight. So we multiply it with W12 superscript 3, which is this weight. Okay, this is how we get the error associated with layer number 2 in unit 2 in layer number 3. And likewise, we can further propagate this error backward. So in layer number 2, let us focus on this particular unit. So we say that the delta superscript 2 subscript 2, which is this error, is computed as these two weights and multiplied by the corresponding error from the previous layer, which is layer number 3 in this case. So we represent it here as W12 multiplied by delta 1, this one. So this could be our W and this could be our W. So this one is W12 and this one is W22 with the superscript 2 here and superscript 2 here. So now we see that this error is computed as a weighted sum of the error from the previous layer, which is layer number 3. And then we don't have any computation for delta 1 because we are not going to change the input values, so we don't compute any delta 1. And now looking at the equations for the forward propagation, so we simply represent them in vectorized form here. So we know that we can set the activation values in the first layer is simply equal to the input, and then in the second layer, which is hidden layer, we compute the weighted sum here, and then we apply the activation function, consider adding the bias term also. And similarly in the next layer we compute the weighted sum, okay, like this in the vectorized form, and apply the activation function. And finally in the output layer, again we just repeat the similar equation and then apply the activation function. So in a similar way, now if we look at the backpropagation computation, we move from right to left, or we say that we move from output layer towards the input layer. So in each output unit in layer number 4, which is the output layer, delta is the difference between the activation in each output unit and the desired output value in that unit. And we can write it in a vectorized form to make the notation a bit simpler here. Okay, so we write it in the vectorized form, and then we compute the delta 3s, the error term associated with layer number 3. So the delta 3 is computed by this equation, where we multiply W3 with the delta terms from the layer number 4, and then perform an element wise multiplication with the derivative of the activation function in layer number 3. So this is actually a vector W3 transpose delta 4, and we are doing an element wise multiplication with this vector to get the vector of delta 3s. And similarly for layer number 2, we can show that delta 2s can be computed as well in a similar way. And this term, the derivative of the activation function g prime z, can be computed by using this equation g prime 3 equal to the activation values in the layer number 3, so a3 with an element wise multiplication done with 1 minus a superscript 3. So now we see that these computations for the error terms, these are rather simple, so we have an efficient way of computing these gradients, and then we can use these error terms to compute our partial derivative for j. Once we know these error terms, we can show that the partial derivative of the cost function with respect to the weights is simply the multiplication of activations in layer L with all these error terms in layer L plus 1. And here, for the sake of simplicity, we are not considering the regularization term lambda. So we assume that regularization is 0 here. So this is now rather pretty straightforward, representation of the partial derivative. So if we summarize the algorithm itself, so for any training data, okay, x and the associated desired output y, we have this matrix of gradients that we set to 0 initially, and then for all the input samples we simply set the input values in the input layer equal to the input itself, and we perform forward propagation going from the input layer up to the output layer here. Okay, then in the back propagation we compute the error term in the final layer, so we compute the delta L term, and then we propagate the error in the backward direction. So we compute delta L minus 1, delta L minus 2 up to the second layer. We do not compute delta 1, of course. And finally we assign this term to our gradient matrix, so we update the gradient matrix by using this equation. So we are multiplying the error terms with the corresponding activation values, okay, and then we add it to the gradients to update our gradient terms. And finally we update and scale this gradient matrix, okay, to get the matrix D, and the matrix D will give us the partial derivatives of the cost function j with respect to our weights w. So this is how we compute the partial derivatives. We see that this technique, back propagation, is giving us a very efficient method to compute our partial derivatives. And once we know the partial derivatives, we can use gradient descent algorithm or other optimization algorithm to the role of the change in W's to the cost function. So by using the equation of the gradient descent, we can update our weights in either positive or negative direction. So another important concept here is the concept of chain rule that comes from calculus. So when we have two functions f1, f2, and the variable is, let's say, w, so if we want to compute the partial derivative of f1 with respect to w, we can represent it as the partial derivative of f1 with respect to f2 multiplied by the partial derivative of f2 with respect to w. But the idea of chain rule is not covered in this lecture, so I leave it here. So I hope that by now, looking at these equations and this explanation, we can develop a good understanding of the algorithm itself and how it is working. But if you are interested in exploring additional resources, there is a wonderful book from Michael Nielsen, so you can look into chapter number 2 particularly, which covers the concept of backpropagation. And also another good resource is the lectures, machine learning lectures from Professor Andrew Ng of Stanford University. So yes, with this I want to wrap up, and goodbye.